DNS and DNSSEC. Welcome to today's training session on the domain name systems and domain name system security extensions. My name is Thoko Miya, and I'm the president and chairperson of the Internet Society South Africa chapter. I'm delighted to be hosting this session. Before we begin, I'd like to briefly introduce the organizations that make this training possible. The Internet Society, ISOC, is a global organization founded in 1992 with a clear mission, which is to ensure that the internet remains open, globally connected, secure, trustworthy. ISOC works around the world to promote internet access, policy standards, and education, with a strong emphasis on multi-stakeholder engagement and community-driven development. Here in South Africa, the Internet Society South Africa chapter brings that mission to life in our local context. Our chapter focuses on strengthening digital inclusion, supporting capacity building in underserved communities, and advancing internet governance, and ensuring too that South Africa remains an active voice in shaping the global internet. We believe in building technical skills, engaging in advocacy, and fostering dialogue across government, academia, and civil society, and the technical community too, of course. In South Africa, within our context, our work is particularly important. While our country has one of the most developed ICT sectors on the continent, digital equality remains a pressing challenge. Many communities, especially in rural and township areas, still face barriers to reliable, affordable internet access. This makes the work of the Internet Society South Africa chapter not only relevant, but urgent. As we strive to empower local communities with both the technical knowledge and governance insight needed to particularly effectively participate in the digital economy. That is what brings us to today's training, the domain name system, or DNS. DNS is often described as the phone book of the internet, translating readable names like example.com into the numerical IP addresses that machines use to communicate. It's a foundational concept of how the internet works, and understanding DNS is essential for anyone working in networking, security, or internet governance. We'll also touch on DNS security extensions, or DNSSEC, which adds a crucial layer of trust and authenticity to DNS queries. In a world where cybersecurity threats are growing, DNS plays a vital role in preventing attacks such as cache poisoning and man-in-the-middle exploits, essentially protecting both the internet infrastructure and our data. A system of DNS evolved from a simple hierarchical lookup service into a complex ecosystem that now supports DNSSEC, privacy, so that's DOT, DOH, performance optimizations like eDNS and Anycast, and deep operational concerns, especially relating to root zone management, registrar, and registry systems. This lecture, this webinar, is going to explain the architecture, data model, resolution algorithms, transport and protocol extensions, security threats and mitigations, governance, operational practices, and current as well as future trends. So looking at privacy, looking at centralization, looking at DNS as a platform. You'll walk away with both conceptual, institutional, and technical knowledge and detail to further understand, operate, secure, and innovate with DNS. So, as an introduction to DNS, what is it and where does it come from? The full story goes that the internet's hidden backbone, for example, when you open a web browser and when you type in a website like www.helloworld.com, you don't really think about what happens behind the scenes. However, within seconds, a page full of information, headlines, photos, labels, videos loads onto your screen. You might imagine that your computer calls this website directly, like maybe dialing a phone number, but that's not exactly how the internet works. What really happens is a fascinating story about translation, coordination, and a hidden system working in the background. That is the domain name system, or DNS. DNS is often described as the phone book of the internet. That's a good starting point if you look at it from this perspective, because the analogy barely scratches the surface of what DNS actually is. But at its core function, it's like a phone book. Think of DNS less like a dusty phone book, but more like Google Maps of the internet. All right? It helps you find where you want to go, but it also takes care of routing, caching, and pointing to nearby servers, and even protecting you from fraud. DNS matters because without it, you would actually need to memorize long strings of numbers, IP addresses, which are example 142.250.72.14, right? So you'd have to memorize that if you wanted to visit Google. But because of DNS and the naming system of the internet, you can simply type google.com. Without it, the internet would be very slow, it would be fragile, and it would be super confusing. The internet wouldn't have grown as much as it has today without the DNS infrastructure. The internet would actually essentially collapse because anybody could trick you into visiting the wrong place. It's no exaggeration, actually, to say that DNS is the internet's hidden backbone, because without it, there actually is no internet as we know it. But most people, even heavy internet users, don't know what DNS is, how it works, or why it matters. It's invisible by design. Your phone, laptop, or tablet quietly consults DNS dozens or even hundreds of times a day on your behalf, usually in milliseconds, without asking for your attention. DNS is like electricity in your walls. It's unnoticed until it stops working. And when it does stop working, the internet seems broken. Think back to the last time when you saw news about a major website outage, Twitter, Facebook, or a big cloud provider suddenly unavailable. Very often, DNS was the culprit, not because DNS itself failed globally, but because a company's DNS settings misfired or an attacker exploited weaknesses. To really understand DNS, we take a journey, first into the history of how naming on the internet evolved, then into the mechanics of how your simple request, like typing www.netflix.com, becomes a full connection to a nearby server. We'll meet the characters in this system, for example, the root servers, registries, registrars, and resolvers. We dig into security, looking at why attackers target DNS and what defenses exist. We look at how DNS affects ordinary people in ways they rarely notice, and explore global politics because naming on the internet is tied to power and governance. And finally, imagining a future together, new technologies, threats, and whether DNS, as we know it, will last for another 40 years. The historical origins and conceptual foundations of DNS lie in the earliest internet, the ARPANET, early TCP and IP. Hosts were identified initially by numeric addresses and a small static host.txt file, maintained centrally and mapped names to addresses. By the early 1980s, this approach did not scale. The number of hosts grew and network topology changed frequently. DNS was invented to decentralize and scale name resolutions with hierarchical delegation and caching, replacing the single host.txt model. Foundational specifications, the canonical technical definitions of DNS, are in the IETF RFCs. These were initially published by Paul Marker-Patrice and basically talk about domain names, the concepts and functionalities. Design principles of DNS are related around hierarchy and delegation. The namespace is a tree. Think of the roots leading towards the TLD, the top level domain, which lead to the second level domain, and going onwards. Administrative responsibility for zones is delegated downward. Authoritative data and caching. Authoritative servers publish records. Resolvers cache answers to reduce load and latency. Extensibility. The protocol was designed to accept new record types and new operational models without foundational rework. Example, UDNSO or new RRs, stateless request response models. Typical DNS over UDP is connectionless, keeping latency low. Namespace, records and zones, the data model. So there's a lot of information, but let's start initially with the namespace. DNS names are sequences of labels separated by dots. terminated by the root label, the empty label. Names are case sensitive for lookups. The root zone sits at the top. Top level domains, usually we call these TLDs, sit, for example, a TLD would be .com or .org, or otherwise a country code, .za, .ng, .us, .io. These are directly under the root. Cover is resource records. DNS stores data as resource records. Important resource record types, so RRs, would be the A/AAAA, which was an IPv4 and IPv4 addresses, IPv6 addresses. It's name servers, authoritative name servers for a zone. It's MX, mail exchange hosts. It's CNAME, canonical names. These are aliases. It's SOAs, state of start of authority. These usually relate to zone metadata serials, and they refresh expiries, timers, etc. TXT, arbitrary text, so used for SPF, DKIM, etc. SRV, service records or service discovery, DNS keys, RRSIGs, DNS, DS, DNSSEC records for cryptographic validation, zone EMID, which is a modern mitigation used along DNSSEC, zones, authority, and glue. So a zone is a continuous portion of the namespace for which a name server is authoritative. Delegation of a name server or zone is expressed via name server records stored in parent zones, plus glue records, address glue, that breaks circular dependencies when a delegated child's name server are under the child zone name. Recursive versus iterative resolution. Recursive resolvers are stubs, clients, recursive resolvers. They accept a query and they fully resolve it, contacting multiple authoritative servers as needed. Iterative or referral steps happen between resolvers and authoritative resolvers. The resolver asks a server and receiver either an answer or referral to a nearby authority. A stub resolver, for example, an OS resolver library, asks the configured recursive resolver. So for example, that would be the ISP or public resolver. If the recursive resolver lacks the record in the cache, it starts at a root server, asks for the TLD name server, then asks the TLD for the authoritative name server for the target zone, then queries that authority with the record, and then the answer is returned and cached for their TTLD. Caching is central to DNS scalability. Every recursive resolver has a TTL, time to life, set by the zone administrator. Caching reduces latency and load, but creates trade-offs between agility, fast updates, and caching efficiency. Classic transport of UDP or TCP, originally used with the initial DNS structure was UDP on port 53 for queries. So that would be fast, small messages. And when a response is too large for UDP, so that's usually exceeding 512 plus minus bytes historically. And when zone transfers, AXFRs are needed, TCP is used. eDNSO extension mechanisms for DNS extend the size and capabilities of DNS server over UDP. eDNS and modern features include eDNS 0, which is RFC 2671 and its successors, and allows for larger message sizes, options, and flags, enabling DNSSEC, additional records, and modern behaviors without switching the TCP as often. DNS implications use eDNS to carry DNSSEC signatures and larger payloads. Anycast server distribution usually looks to root and major public resolvers. These use Anycast routing to run many geographically distributed servers sharing the same IP addresses. Anycast improves latency, fault tolerance, and DDoS, resilience by directing clients to the nearest instance. IANA and ICANN document the authoritative root server system. and it's distributed any cost backed implementation. So IANA provides +1 operational ecosystem registries, registrars, and operators. What exactly is a registry and what exactly is a registrar? Registries operates a top-level domain. So, for example, Verizon operates .com and maintains the authoritative data for that top-level domain. A registrar interfaces with registrants, customers, to sell or manage domain names and coordinate with the registry via delegated APIs. For example, when you and I, registrants, buy on the internet our specific named domain names. For example, maybe I go on the internet and I purchase Thoko.com. I buy that from a registrar. That is the person who sells and manages the domain names as well as coordinates with the registry and the delegated APIs. The registry here would be Verizon for .com. Root zone management is also coordinated through IANA and ICANN functions, and the root zone is distributed to the root server operations. The root's contents are what you call its delegations and are the foundational starting point for resolution. Since 2016, the stewardship of IANA functions transitioned away from NTI oversight to multi-stakeholder governance. Operational details are documented by IANA. The resolver operators and public resolvers, recursive resolvers operations include ISPs, enterprises, and public resolvers. Public resolvers include Google Public DNS, Cloudflare 1.1.1.1, and also the Quad9, for example. Public resolvers change the threat and privacy calculus because they centralize query metadata. DNS security threats and mitigations range across a variety of spectrum, including cache poisoning. Attackers inject forged documents into caches that resolvers return as bogus answers and redirect users. In 2008, the Kaminsky vulnerability reignited focus on DNS security. Its disclosure prompted widespread mitigation efforts, including source port randomization and accelerated DNS-sec adoption recommendations. Dan Kaminsky's blog. Amplification of DDoS. Attackers, in this instance, spoof a victim IP, right? And send small queries to open resolvers, eliciting much larger responses for flood victims. Another example is the man in the middle. On-path observers can eavesdrop or tamper with plain DNS over UDP. DNS-sec, cryptographic origin and integrity. DNS-sec, so the domain name security extensions, adds digital signatures. So recursive resolver signatures, RRSig, key records, DNS key and delegation signer, DS records for DNS data. DNS-sec protects against forged responses by allowing resolvers to cryptographically validate the chain key from the root down to the signed zone. Specifications and best current practices are defined across RFCs. For example, RFC 4033 to RFC 4035, and later best practice documents. DNS deployment reduces certain attack classes, so poisoning, but introduces operational complexity like key rollover, signing, and other larger responses. Two major standards encrypt and transport DNS to prevent passive eavesdropping and tampering. So that would be DNS over TLS, DOT, and DNS messages carried over TLS, typically on port 853, as well as RFC 7858, carried in an HTTP or HTTPS exchange through RFC 8484. So DOT and DOH aim to provide confidentiality and integrity for DNS queries between clients and resolvers. They raise operational and privacy policy changes. They centralize resolvers and also learn many client queries, especially in enterprise networks where they prevent visibility loss. Privacy is one of the biggest topics around DNS, and privacy improving behaviors and techniques include the queue name minimization. Resolvers send only the minimum necessary portion of the query name to each upstream server to reduce leakage of full query names. So RFC 7816. This mitigates unnecessary exposure of the full FQDN to intermediate authorities. You can find more information about these topics through the IATF. Operational reactions to non-compliance. So for example, DNS Flag Day, which took place in 2019, coordinated by major resolver vendors, removed long-term workabouts for broken authoritative servers. The community used the event to encourage standards compliance and reduced ossified fragile behavior from the DNS ecosystem. Anycast, caching, hierarchy, and TTL strategy performance relies on caching strategy and server distribution. Anycast improves client proximity, and administrators must set TTL's balancing responsiveness to updates against improved cache hits. Authoritative operators often use multiple geographically diverse instances behind Anycast and multi-host setups, and may use secondary providers, CDNs, and managed DNS providers for resilience. So CDNs and DNS as a control plane, actually content delivery networks use DNS-based traffic steering via short TTLs, geolocation, aware authoritative responses, and DNS zero, client subnet options to direct clients to optimal edge nodes. This takes DNS not only name resolution, but an active performance and traffic engineering control plane. This technique also raises privacy concerns. eDNS client subnet ECS leaks client subnets info to authoritative operators and has been controversial. Measurement, observability, and analytics around DNS play both a vital telemetry source and privacy risk understanding. Operators and researchers use DNS logs for performance and health monitoring, detecting compromises or DNS traffic anomalies, studying global domain name resolution trends, domain abuse analysis, malware C2 phishing, and at the same time, storing and analyzing DNS query logs creates privacy responsibilities. DNS, therefore, is not only a technology, it needs to be governed because of the way that we use it. And it's governed by multiple stakeholders, including IANA, who govern at the root and also govern TLD administration and policies, same with ICANN. DNS is further governed by registries and registrars, commercial and contractual frameworks for domain allocation and pricing, as well as content takedown, which takes place at a national and international law level and enforces basically standards bodies, IATF, regional internet registries, and late registrar ecosystems that create concentrated economic power in parts of DNS pipelines. Market events and corporate shifts can have downstream effects on domain name costs. So encrypted DNS, so DOH and DOT, migrates queries from the cleared to encrypted channels, protecting users from on-path observers, but also moving query visibilities to resolvers or centralized DOS providers. Enterprises and network operators worry about losing DNS visibility for security controls, content filtering, malware detection, etc. So simultaneously, privacy advocates argue for minimizing exposure and metadata collection. Centralization and large public resolvers mean that many clients now use few large public resolvers. Centralization delivers performance and security advantages. For example, rapid mitigation of operational incidents that increase concentration of trust and potential for surveillance and data misuse. DNS is programmable and informs part of geopolitics. It's increasingly a programmable layer. APIs, for example, for dynamic records, geolocation for steering, and integration with orchestration. So Kubernetes, external DNS controllers, these national scale policy decisions, exercising content takedown or partitioning, bring geopolitical concerns about control of naming and access. Automation of DNS signing, example through ACME-like mechanisms, or automated key rollover tooling, automated provisions via APIs, so WHOIS registry and protocols, and continuous delivery for DNS records are maturing best practices. DNSSEC relies on public key cryptography in the long run, and quantum computing poses a theoretical threat. The community is exploring post-quantum algorithm migration strategies and hybrid strategies to maintain trust chain. New record types and integrity features, tech like Zone MD, Zone Digest, complements DNSSEC to verify zone contents, and new RRs.